Okay, section 5.4 on page 471. If you have a book, we're going to do only two pieces of this, the double angles and the half angles. So if you have the half sheet that I gave you, you're going to want to have that out to take a look at. We're going to deal with some double angles here first. And the very first example is showing how double angles work a little bit, but at the same time proving it. So this is our double angle formula. If you'll see on your half sheet, we have that the sine of 2x equals 2 sine x cosine x. We're going to try to prove that. It's not very hard. It falls out really fast. If you understand that what we want to do is work on this side by writing it as something we know, which is x plus x, because we've worked with the sign of a sum. So we write that 2x inside parentheses as x plus x, and then keep spreading that thing out, which would be sine x, cosine x, plus cosine x, sine x. And yes, these are backwards, but we can multiply in any order we want. So what we really have here is two things that are exactly the same. Voila. So that's proof of the sine of the double angle. And it shows you that you may want to take the 2u and possibly the 3 plus u or something. Okay, the next thing the author does is goes to these power reducing formulas. I really don't want to do these. It's on page 472. The power reducers are not something we're going to study. So I'm going to go over to demonstrate what we're going to do here with these double angles. I'm going to be bouncing around here a little bit because they throw in the double and the half angles all over the place here. So everybody go over to example 4 with me so we can stick with the theme for just a minute. I know, I'm going to be bouncing around here. Example 4 on page 474 says solve. So we're not proving an identity or anything. We're going to solve algebraically on the interval from 0 to 2 pi. Hallelujah. We're going to have the z thingy, the n. They just want us to solve in the first go around the unit circle, sine 2x equals cosine x. Now, rather than do what I did to this here and write this as x plus x, I don't want to default to that. I've already proved what that is, and it's 2 sine x cosine x. So I'm going to replace this with this actual identity, which is 2 sine x cosine x on your paper. So it's just a replacement using an identity. And then, since we're trying to solve, we're not proving an identity or anything. We're trying to solve this thing. We want to get everything on one side. You never want to cancel a cosine out of both sides. I know that's very tempting, but if you do, you'll be canceling solutions. So don't do that when you're solving. Leave everything there. Don't cancel anything out. Bring the cosine x over by subtraction. That way we haven't lost anything. Then you factor that out, and you end up with 2 sine minus 1, because if you take all of a term out, there's still a 1 there to hold its place. And then when you're done factoring, each one of them gets their shot at being 0. That one right there, the cosine, I'm asking myself, what x value will give me a cosine of it that's equal to 0? And this one, if you do the algebra in your head, is asking when is the sine of x equal to 1/2? Is that good? Now remember, we're only going from 0 to 2 pi. And so I want to know, after I go around the unit circle, when is the cosine of x equal to 0? And if you'll remember, it's when it's straight up and straight down, because that's when sine is 1 and -1, cosine's the other. So x equals pi halves and 3 pi halves. Could I call that negative pi halves instead? No, not be in that interval. Okay, so don't, it has the same terminal side as this, but if you're going to be in that interval, you have to go around 3/4 of the way around to get the 3 pi halves because it fits in this interval. You see what I'm saying? Okay, and then the sine of x equals 1/2. I'm going to need to look in the first and second quadrant because 1/2 is positive, and that's where sine is positive, is first and second. And if I draw myself a triangle, I'm looking for a triangle whose opposite side is short, which is 30. So x is, 30, it's pi sixths. And also in the second quadrant, like that, and that's where this is 5 pi sixths. All of these angles will make that equation true. Do you want to see? No? You believe it? Okay, that's fine. Okay, now, it's going to seem like I'm not giving you much of a lecture or helping you out much. You are familiar with identities. If you see the sine of 2x, you can replace it with what it's equal to. If you see 2 sine x cosine x, you can replace it with sine 2x. You already have dealt with identities, so there's not a lot of examples in here. So that's all you get on the double angles. Okay? The half angles are on page 473, but they're also on your page here. Tangent, as you can see on page 473, the tangent of a half angle, half of an angle, is got three things there. And we've only got one example dealing with that. I think. Yep, only one. And it's example 5. This is mainly, because you got the recipe, you were taught how to use recipes yesterday, now there's not much to show you. Maybe 1 or 2 examples, give you a couple of little hints, but there's just not much here. So we're going to do a half angle one, and then you're going to go to work, and you're going to let me know if you have individual questions on what you're doing. There's just not much here that's new. So in example 5, it says, solve the equation again. We're solving again. Sine squared equals 2 sine of x over 2. Is that right? Did I get that right? Yes, sine squared. Sine squared on both sides. Okay.
Wait, where are you looking at?
I'm looking at example 5, just before the exercises. Page 474. Okay. So now this one does get a little bit tricky. Do you see the sine of a half angle on your paper? It's right here. Let me ask you this. If I have the sine of x over 2 and it equals the square root, I'm just using the identity, I'm writing it down exactly like it is. 1 minus cosine x over 2. If I squared both sides, wouldn't that just peel that off? So what I have here is 2 times this fraction. Because I have sine squared of x over 2 right there. I have sine squared of x over 2. And I just showed you that if you square sine of x over 2, you square the square root off of it that's in the identity. Do you understand? And so what I have is right here is 2 times 1 minus cosine over 2. But that's a really happy thing too. That just cancels. So what I'm really left with is sine squared equals 1 minus cosine. That whole thing is just 1 minus cosine, according to the identities. If you square both sides of that half angle, which is what's happening right here, then the radical doesn't even show up, which is nice. It happens that way a lot. They square things a lot. They square those things right off. Okay, so we've got this now, and you're going, I don't know how to solve that. It appears to be quadratic-y, right?
What about the sine squared? Shouldn't it be x divided by 2 on the left side?
Here?
No, on the other side. So
Over here?
Yeah.
That's just sine squared. There's no multiple of the angle there. This is just sine squared. There's no identity. Well, there is an identity, but not one we're learning about today that can replace this.
Okay.
This one, that piece right there, that one right there was this one over here. That was the square root. And I'm saying that the sine of x over 2 equals the square root is saying exactly the same thing as saying the sine squared of x over 2 is equal to that fraction. So there's the 2, and that's the sine squared of x over 2 is just that fraction, 1 minus cosine over 2. Okay or not?
Okay.
Yeah? Yeah? And then the 2's cancel. And I'm left with this. You go, well, how do I handle that? It's quadratic-y, but this is sine squared, and that's cosine. It's always, always, always easier to replace your squared stuff than your single stuff. So I'm going to replace that with 1 minus cosine squared from before. Remember? The reason I'm doing that is so that this thing can be written in terms of one trig function, and we can apply our quadratic methods to it.
Wait, how did you get the 1 minus cosine?
Because this is always true. And so sine squared is equal to 1 minus cosine squared. That's something you want to remember really clearly, because that shows up all the time. Replacing squared things with something they're equal to is way easier than replacing single things, because it ends up having a square root in it if you try that. Okay. Everybody clear on this little move?
Yeah.
Notice that the ones add out, and I'm left with negative cosine squared equals negative cosine x. Because if I subtract 1 from both sides, I'm left with this. And if I divide both sides by negative, I get this. I'll leave them on there if you want. So I'm going to bring everything over to one side. Well, actually, I'm not going to leave them on there. I'm just going to write down the next line so that you can see. This is the same thing as cosine squared equals cosine x. Because you divide both sides by negative. The ones added out to get to here. Everybody clear? This algebra is not that hard to follow. Just got to wake up and stay with me. Okay, so we don't cancel a cosine out because we don't cancel in the process of solving. We bring everything over to one side and factor. And what comes out of here is a cosine. So the question is, when is the cosine of x equal to 0? At pi halves and 3 pi halves. What is the cosine of x? The next one is, when is the cosine of x equal to 1? 0. Now, did they want it just want to go around the inner circle, or no, it says solve it. Crap. Okay, so I want you to see where these solutions show up. We've got one of the solutions right here, one right here, and one right here. And those are not evenly spaced like the propeller of a plane. They're not evenly spaced, but these two are. So to write our final answer as efficiently as possible, we would write for the 0, which is the one that's the weird one sticking out to the side there. You don't say 0 plus 2 pi n. You just say 2 pi n. That comes from this one. Another solution is pi halves plus 2 pi n. And actually, okay, think about this. If the solution is pi halves and I've already arrived there, then if I add 2 pi n, I'll get that one again. And I'll get it again and again and again. But if I just add pi n, I'll grab this one on the way every time. I get myself up to here and then I go add pi. Okay, add pi, add pi, add pi. So I don't have to list the 3 pi halves one, because as soon as I list pi halves plus pi of any sort, I'm going to land at that 3 pi halves at that terminal side. So this is it, where n is an element of the integers. So if you look at your solutions and see, every time one's just exactly opposite the other, you're just going to be adding pi to get to it. Okay, that's all you get. Take this, try to run with it. Let me know if you run into any trouble.
There we go.